Assalamualaikum and very good day to Associate Professor IR Dr. Syaril Irwan. My name is Ahmad Eimran bin KAMARUDIN. Today I will be presenting assignment 3 for the course EEE 640. The title of the assignment is Grid Connected Photovoltaic System Design for a Residential House in Shah Alam, Selangor. Nowadays, the demand for electricity is continuously increasing due to population growth and the increasing use of electrical appliances. At the same time, renewable energy has become an important role to reduce dependence on fossil fuels and lower carbon emissions. Malaysia is fortunate because we receive abundant sunlight throughout the year. Therefore, solar photovoltaic technology is one of the most suitable renewable energy sources for residential applications. For this assignment, I designed a complete grid-connected photovoltaic system for a residential house located in Shah Alam. This design includes site assessment, component selections, PV array configurations, energy output estimations, and the electrical schematics of the proposed system. Moving on to the objectives of this assignment, there are 4 actually. The first objective is to design a grid-connected photovoltaic system that is suitable for a residential house. Second objective is to assess the installation site by evaluating the rooftop area, shading conditions, and solar potentials. And the third objective is to select suitable photovoltaic modules and inverter that are compatible with each other while satisfying the electrical requirements. Finally, the 4 objectives is to determine the PV array configurations, estimate the annual energy generations, and develop the complete electrical schematic of the proposed system. Overall, this objective is to ensure that the designed PV system is technically feasible, efficient, and suitable for the selected residential house. Moving on next. This slide presents the site assessment of the proposed installation locations. The residential house is located in Shah Alam, Selangor, which has a tropical climate and receives relatively high solar irradiation throughout the year. Using Google Earth, you can see here, I measure the value of the rooftop that is suitable for PV installations, and the selection roof has an area of approximately 65.14 square meter. I also evaluated the surrounding environment to determine whether shading will affect the solar panels. Although there are trees around the house, they are located far enough from the selected roof and are not expected to create significant shading during peak sunlight hours. Based on these observations, the selected rooftop is suitable for installing a grid-connected photovoltaic system. Moving on next. Before selecting the PV system size, I analyzed the household electricity consumption using the latest 2 TNB electricity bills. The first bill recordedly monthly electricity consumptions of 1,273 kilowatt hours, while the second bill is recorded around 1,914 kilowatt hours. These values indicate that the house has relatively high electricity demand. By understanding the monthly electricity consumptions, I was able to estimate the appropriate PV system size that can offset a significant portion of the electricity supplied by TNB. Therefore, installing a grid-connected PV system is expected to reduce electricity bills while improving energy efficiency for the homeowner. Moving on next, the component selections. After completing the site assessment, the next step was selecting suitable components for the PV system. For the photovoltaic module, I selected the Longi High Mo 6 LR572HTH 580M. This module has a maximum output of 580 watts and a module efficiency of 22.5%. It also provided excellent durability together with a 25-year performance warranty, making it suitable for long-term residential applications. For the inverter, I selected the Huawei Sun 2000 10 KTL M1. This is a 10 kilowatt 3-phase grid connected inverter equipped with two independent MPPTs, allowing the inverter to maximize the output for each PV string. The inverter also has a maximum DC input voltage of 1100 volts, high conversion efficiency, and intelligent monitoring capability. The selected PV modules and inverter are electrically compatible and satisfy the design requirements for this assignment. For the PV array configurations, after selecting the components, I designed the PV array configurations. Based on the available rooftop area and inverter specifications, I selected 18 photovoltaic modules. The modules are arranged in two strings with 9 modules connected in series for each string. Each string is connected to one MPPT input of the Huawei inverter. This arrangement allows both strings to operate efficiently while keeping an operating voltage and current within the inverter's allowable limits. The total installed capacity of the PV system is around 10.44 kilowatt peak, and the configuration efficiently utilize the rooftop space while ensuring reliable system operations. For the annual energy output, using the selected PV modules, local solar irradiation data for Shah Alam, and system efficiency factor, I estimated the annual electricity generation of the proposed PV system. The installed capacity of the system is 10.44 kilowatt peak. Based on the calculations, the expected annual energy generation is approximately 13,666 kilowatt hours per year. The calculated performance ratio is 83.66%. The performance ratio represents the actual performance of the PV system after considering losses such as temperature effects, inverter efficiency, cable losses, and other environmental factors. A performance ratio above 80% indicates that the proposed PV system is operating efficiently. Looking at the electrical schematic. This slide shows the proposed electrical schematic of the grid-connected photovoltaic system. Starting from the left, electricity is generated by 18 photovoltaic modules, which are arranged in two strings of 9 modules. The DC output from both strings is combined inside the DC combiner box. Then the electricity then passes through the DC surge protection device, which protects the system against lightning and voltage surge. Next, the electricity flows to the DC isolator, allowing the PV system to be safely disconnected during maintenance. And after that, the DC power then enters the Huawei Sun inverter, where it is converted into 3-phase AC power. On the AC side, the electricity passes through the AC surge protection device and AC isolator before entering the MDB. And finally, the electricity is applied to the household electrical loads through the MDB and connected to the 3-phase TNB meter. Whenever the PV system produces more electricity than the house requires, the excess energy can be exported to the TNB utility grid. If the PV generation is insufficient, electricity will automatically be imported from the grid. This configuration ensures safe, reliable, and efficient operations of the grid-connected photovoltaic systems. The proposed grid-connected photovoltaic system provides several important benefits. From an economic perspective, the system can significantly reduce monthly electricity bills by generating electricity from solar energy instead of relying entirely on the utility grid. From an environment perspective, the use of solar energy helps reduce greenhouse gas emissions and support the transitions towards cleaner energy sources. From a technical perspective, The selected components provide high efficiency, reliable operations, and safe integrations with the existing three-phase electrical system. Overall, the proposed system supports Malaysia's renewable energy initiatives while promoting sustainable energy usage in residential buildings. To conclude, these assignments successfully demonstrate the complete design of a grid-connected photovoltaic system for a residential house located in Shah Alam, Selangor. This design includes site assessment, electricity consumption analysis, component selections, PV array configurations, annual energy estimations, and the electrical schematic of the proposed system. The final design consists of 18 Longi HIMO 6 photovoltaic modules, together with a Huawei Sun 2010 KTL M1 3-phase inverter, giving a total installed capacity of 10.44 kilowatt peak. Based on the design calculations, the system expected to generate approximate 13,666 kilowatt hours of electricity annually with a performance ratio of 83.66%, indicating good overall system performance. Overall, this proposed system is technically feasible, suitable for the selected residential house, and capable of reducing dependence on electricity supplied by TNB while promoting the use of renewable energy. That concludes my presentation. Thank you for your attention and thank you.